Okay, so welcome back everybody after a short break. I'd like to give a warm welcome to Marni Mishna from Simon Fraser University, who's going to talk about lattice walk enumeration, analytic, algebraic, and geometric aspects. So over to you, Marni.
Thank you very much, Mark. I hope you can hear me and see my slides fine. Thumbs up.
Yeah, it's perfect. And your audio is perfect too.
Excellent. So first I want to thank the organizers and Tufik for a very well curated event. And I guess I get to be the third arm of the Canadian trilogy there. It looks from my title that I'm going to be talking about lattice walk enumeration. Lattice walks are going to be the vehicle by which I'm going to talk about generating functions and classifying functions. And I'm going to focus on transcendental functions, okay? But hopefully it will all be clear. So the theme, I think, for enumerative combinatorics in general, but in this talk in particular, is that there is a certain duality between combinatorial complexity and algebraic and analytic complexity of functions. And so let's first think about why we might want to use that. Well, if we go back to some of the original number theoretic problems, number theorists were interested in numbers and they wanted interesting numbers. And rational and algebraic numbers, they're very computable, they're very manipulatable, but they're also they're not that complex, right? And the full set of complex numbers, it's somehow too large. So the solution for number theorists was to consider periods. So this is a number that can be expressed as an integral of an algebraic function over an algebraic domain. They're encoded by a finite amount of information, and they can be identified in an algorithmic way. And it contains a lot of the interesting numbers that we like zeta constants and pi. So that was somehow a good solution by the number theorists. Okay. So Hilbert in 1902 remarked a similar deficiency in the study of complex analytic functions. So rational and algebraic functions, they're certainly interesting, but they're a little bit limited, right? So a solution or a consideration was to add what I will define in a moment as these D-FINITE functions and differentially algebraic functions. They have properties of countability and they're good for algorithmic study, but they're actually still a little bit unsatisfying, as Holder had already shown in 1887 that the gamma function wasn't differentially algebraic, and that was something that they really wanted to capture. But nonetheless, I'm going to talk about these two classes, okay? And again, the lattice walks are going to come in, I promise. But I'm going to focus on the class of D-FINITE functions and somehow that boundary of differentially algebraic and the things that are beyond that, okay? So I'm really interested into seeing how combinatorics is going to give us some insight on this fundamental structure. Okay, so I'm really quite motivated by function classification, but I like to play with lattice walks, so that's what we're going to do today. But first, let me give a bit more of definition of these two classes, just to make sure we're all on the same page. Okay, so I'm calling them transcendental classes because they're things that are not algebraic. So the first one was D-FINITE, differentially finite, and here you satisfy a linear differential equation with polynomial coefficients. Okay, so there's an example of an order 2 sort of thing on the side there. Differentially algebraic is a slightly wider class. It doesn't have to be linear anymore. You satisfy some sort of polynomial differential equation. And I'll say that you're differentially transcendental if you're not differentially algebraic. Okay, so we typically take out the differentially, and if you notice closely, one of them is differentiably and one of them is differentially. So let's just simplify it and call them D. So we have D-FINITE, D-algebraic, and D-transcendental. Okay. All right. So now let's take a look at the combinatorics. So recall, and I think in this audience, hopefully, you're familiar with the ideas of a generating function, and I assume that we all are. But we'll have a combinatorial class. It has a size function, an ordinary generating function encodes enumerative data. Okay, much like we had in the last talk, we had the power series with accounting information and the coefficient. Okay, but I'm interested in, I mentioned this because I'm specifying that I'm talking about ordinary generating functions. Okay, so what's been well known for a long time is that if I have a finite class, well, the generating function would be a polynomial. If it's some kind of iterative class, where it's recognizable by a finite automata or a regular language, it's going to have a rational generating function. If it's a recursively specifiable class or something they call an algebraic class, things that generally have a tree structure, the generating function is algebraic. And so it's been sort of a long-standing question now. Is there a type of class which corresponds naturally to D-FINITE functions? Is there a class which corresponds naturally to D-algebraic functions? Can we identify combinatorial mechanisms when things should be differentially transcendental? Okay, so here are some examples of which we'll come back to in a moment. This correspondence isn't entirely perfect, and somehow the holes are actually very interesting, but that's a subject for another talk. Okay, so I'm interested in looking at these two bottom classes and trying to understand combinatorial criteria for these transcendental classes. Okay. So why should we do that, right? So why would we expect that would be interesting? We could invent any sort of class, and in fact, this happens on a daily basis in our fields, in mathematics. Why would these D-FINITE functions be useful from a combinatorial perspective? Well, there's a lot of evidence that there should be. There's a lovely quote that I like by Flageolet, Gerhold, and Salvi saying that almost anything is not holonomic unless it's holonomic by design. So holonomic and D-FINITE somehow overlap in the generating function world. So that's saying something about D-FINITE functions or suggesting something about D-FINITE functions. There's closure properties, which mirror combinatorial actions. The differential equation itself is a very useful data structure. We're interested in, the last two talks had some computer algebra or computing going on in the background. These give us something to which we can grip onto. There's some clear proof strategies, and there's some interesting open conjectures about what these D-FINITE functions should be. So Crystal in 1990, which already starts to be a little while ago, said that it would have to be that under certain conditions of convergence, the D-FINITE functions should be diagonals of rational functions. That's a very combinatorial sort of description. So this is still open. Okay, but differential algebraic, well, they're a lot more difficult to manipulate and characterize. You can't do the same sort of guessing. They're a lot trickier to manipulate. But what I'm going to show to you by the end of today is that we do have lots of criteria to show when you would not be differentially algebraic. And that's going to be what I think is going to be our entry point as combinatorialists. Okay. So there's some evidence that these are very useful classes. So when I say there's proof strategies, it means I could give a class to a grad student and say, first, do some general counting, see if you can guess, see if you can find a reflection principle, see if you can find an infinite number of singularities, see if you can find the asymptotic growth. And if you do the first two, maybe you can show that the function is D-FINITE. And if you do the second two, maybe you can show that the function is not D-FINITE. So there's actually things that you can try, which is good, especially when you have to find good problems, good entry problems to an area. Okay. So of course, you could also find an explicit expression and find the actual differential equation. Okay, so D-FINITE functions are interesting. In combinatorics, well, of course, like I said, they were sort of defined, already in the 19th century, but they hooked on in combinatorics because of Richard Stanley's 1980 article, Differentially Finite Power Series. And in there, he plants several seeds of saying like, hey, these are going to be interesting and look at these class. So he looks at Baxter permutations, Young tableau of bounded height, and K-regular graphs. Okay, so I think within 10 years, there was a lovely paper, one of my favorite papers of Ira Gessel, showing that the Young tableau of bounded height were D-FINITE. And also the K-regular graphs were D-FINITE for a fixed K. Baxter permutations were already known at that point, I believe, but trying to find a coherent theory that tries to unite some of these ideas, well, that's still rather open. Okay, so I found 16,000 hits on D-FINITE functions on Google Scholar since 1980. So that's again, somehow evidence that this is a very active field. Okay, so keep in mind these initial seeds here. Okay, but now I'm going to move. I mean, I looked at this as early as my PhD, this problem, and it's really too big of a world to work in from my perspective. So I narrowed in to lattice paths when I went to work with Marni Bousquet-Milou, already almost 20 years ago. And that gives you a little laboratory where you can build functional equations and you can start to build objects, and they're very easy to manipulate. They're very easy to understand, and they actually encode a fair number of classes. So let me just tell you what I mean by lattice walk and why, how I'm going to get the generating function. So I'm going to consider walks on, let's say, this integer lattice, and I'm going to consider a finite set of steps. So can you, Mark, can you see my pointer? I can never remember if you can see the pointer when I'm in. I think you can't when I go in. Can you see it? Yes, okay. So here I'm saying that I'm going to take walks starting at the origin, and I can go north, east, south, and west. And if I code each direction by a little term, okay, so basically x, then if I multiply those terms, then I'm going to get the generating function for all possible endpoints. Okay, so what do I mean by that? So if I multiply this twice, I get somehow an inventory of all the walks of 2 steps, and I see I get 2xy, and this is from going this way and this way, and this way and this way, and ending at the point 1, 1. So this is x to the 1, y to the 1, and I've got 2 ways to do it, and I can capture that by just multiplying these terms. So if I'm interested in enumerating walks that are unrestricted in my plane, well, then I could just use that geometric series. I'm going to add a t to keep track of how many steps I've taken. But really, the generating function for all walks in an unrestricted way, it's a simple rational function. And I'm just multiplying these things, however many times for steps I'm taking. So that's really straightforward. So that's somehow too straightforward. Let's add some, before we say add on to complexity, let me just say that we're going to bound the regions. We're going to do a bunch of things, but walks already in themselves, although it feels rather arbitrary, they're very effective for modeling cues. There's a whole branch of walks, which is just trying to give you information of cues. There's another school which uses these to model polymers and try to predict things like phase transitions. And then actually have a lot of really interesting bijections. Say Baxter permutations, I can encode that as a lattice walk family. Young tableau of bounded height is a lovely paper. Even I think Doron has looks at this in some general height, and just finding the class of lattice paths that encode the Young tableau of bounded height. Okay, so here again, you might have to go up to higher dimension. You're going to have to go to higher dimension, but the point is that lattice walks actually can encode many of the classes that we're interested in. We've already seen these Baxter permutations, Young tableau in Stanley's list. So already we're kind of happy. Okay, so I'm going to actually make my world even smaller, and I'm going to look at small steps in the quarter plane. So what does that mean? I'm going to look in Z2, but actually I'm going to look in only things in walks that start at the origin and end somewhere with a non-negative coordinate. I'm going to fix a finite step of walks, and the steps are all going to be somehow unit steps, okay, unit in any direction, okay? I can build a generating function where I track, like I was doing before, the endpoint. And the point is that there exist some non-D-FINITE models, and we'll come back to those in a second. And in fact, I did quite an exhaustive study with Marni Bousquet-Milou, and we said that even though you have a lot of different possible models here, once you exclude some of the ones that are in bijection, the ones that are trivial, you have 79 non-trivial distinct models, okay? So I'm looking for subsets of this sort of extended compass here. That's going to be your step set, but there's only 79 distinct models, and this is enough to do a very comprehensive study. Okay, and we noticed a correlation about the D-FINITEness of the counting generating function and a related group. Okay, so D-FINITEness, oh, pardon me, I wrote holonomy here, but I did mean D-FINITEness, is correlated with some group, a geometric group that I'm going to show you a picture of in a second. So the question is, what is the nature of this series can we use the combinatorics of these objects to understand the classification of different series? Well, this led to a decade-long international collaboration with all sorts of beautiful techniques from complex analysis, computer algebra, differential Galois theory, and there was a classification of the multivariable generating function, keeping track of the endpoint. Okay, so which ones are algebraic, D-FINITE, differential algebraic, differentially transcendental. Okay, so that's a beautiful story to have a complete classification of these 79 models. And we had conjectured that when this group, which I have not described for you yet, but I'm going to show you a picture, when it's finite, that's going to give you the structure that you need for the generating function to be D-FINITE. Okay, and that turned out to be true. Okay, so let's go into what this group means. So we said that D-finiteness appeared to be, and then it was confirmed that it's correlated with a certain group. This is where we get the geometry of the title. So it's a group of birational transformations that fix the inventory of the step set. Okay, so what does that mean? That's a little bit blah, blah. Here is a polynomial, which is just keeping track, a little generating function of the steps. So this is a polynomial because my allowable steps are finite, and it's a little well, I guess this is a Laurent polynomial. And let me actually do an example, because trying to do this in general is probably too much at this point. So imagine I have my northeast, southwest. Remember those I had encoded each possible direction by a monomial. So we've got them here. And this is what we had in the denominator of that rational function. So this is my kernel. And what I mean by a birational transformation is I mean something that's going to fix this. So certainly if I send x to 1 over x, that's going to fix it. And if I send y to 1 over y, well, that's going to fix it as well. I could swap x and y, but that's not actually useful for me. Okay. So I'm interested in these kind of do something to x, do something of y. That's the bi, and there something is something rational. So that's the birational. So it turns out that if I can turn this into a group, when I can visualize this group. If I look at the zero sets, the compactification of the zero set of this kernel, I can actually build an algebraic curve. Okay, for small steps, it's always going to be genus 1 or genus 0. Now we're starting to get a little bit heavy, so let's think about what we're talking about here. So remember, so in some cases, this zero set is going to be an elliptic curve, and then this group action I've got here is actually going to be the group action on the elliptic curve. But let's actually see an example. So my northeast, southwest, I have my kernel. I'm interested in complex solutions, but here are the real ones. Here are the real solutions to that curve. I've evaluated for an event where I've evaluated t at a specific value. So I said this group was a group of order 4. Oops, where'd it go? Oh no. I don't know what happened there. Okay, here we go. So here is the takeaway that you can jump to right now if the last bit was a little bit hairy. For every step set, I have a curve, and then I'm moving around this curve, going straight up, going straight across, till I hit the curve and I come around. So in this case here, I can do it in 4. I get back to where I'm starting in 4. So it's a group of order 4. Some groups are going to be infinite. They're going to sort of go off to infinity into the corner. But when the group is finite, I know it's going to be a maximum group of order 8. And I can actually pull a lot of information from this curve, like determine if something is D-FINITE or algebraic. And I can get criteria for it to be differentially transcendental. So this is the geometry of a lattice walk. I look at the inventory of this step set. I'm building a curve, and I'm interested in how I can move along this curve. Okay. And the way I'm moving along this curve, it's very much the same way as, remember, if you've ever done, when you add 2 points on a curve and an elliptic curve, that's really the same thing that we're doing here. Okay. Okay. So the geometric understanding of that kernel solutions actually gives you a lot of combinatorial results. I think that's really beautiful. I really love that story. Okay, so now let's go back to our question of differential transcendence and D-finiteness. But actually, we're gonna work on that boundary now, that differential transcendence. So here's a rough principle, and there's a lot of caveats, and I'm not going to go through them here. But if you want to, if you love reading those sort of caveats, the article of Adam Chesky, Dreyfus, and Hardwell of 2021. It's beautiful. It's absolutely beautiful, and I highly recommend it. But here's a rough principle. Imagine I have a solution of a linear shift, Mahler, or Q-shift equation. I'll give you some examples in a second. Well, then you're either going to be really, really simple. You're either going to be a rational function or differentially transcendental. So what is this principle? And this is my main takeaway for today, is that if you want to satisfy a differential equation, you really can't satisfy other kinds of equations unless you're very trivial. Okay, so let's look at some examples. So the shift, by the shift, I mean the gamma function satisfies the shift equation. Okay, I've got a shift in the variable here in the evaluation. We know the gamma function is not rational, so by this principle, it must be differentially transcendental. Okay. The Mahler operator is when I substitute x by x to the power k. So if I have this series here, x to the 2 to the n, I can write a nice little Mahler equation, a linear Mahler equation. So either this function is rational, but we know that it's not. So it must be differentially transcendental. Okay. Here's another example. I can do this shift where I send x to be x over 1 plus x. So Klazar wrote something for the ordinary generating function of the Bell numbers, not the exponential function. Got a nice linear equation using this operator. And then, although it actually sort of follows by some other things as well, but Bostin, Division, and Rachel, they have a recent paper which looked at this operator explicitly. And again, we have the same sort of thing, that if you satisfy this kind of equation, then either you're trivial, or by trivial, I mean rational, or you must be differentially transcendental. And the connection to lattice paths is that you can, I'm going to show you, well, I'm not going to walk through it. I'm going to show you in one slide that if you have a Q shift where Q is a number and not a root of unity, you either are going to be rational or you must be differentially transcendental. And we're going to look at these walks and show that they must be differentially transcendental. So what I like about this, I think it's beautiful because the mathematics is gorgeous. It's like 120 years of mathematics sort of summarized here. These are all very combinatorial operators too. Shifts, we have a good understanding of what this may or may not be. So I think there's a lot of potential to really understand differential transcendence, even though differential algebraicity, I think, is very difficult to wrap your head around. Okay. So again, that's my main that's one of my main punchlines for today. So if you need a break, take a break. But if not, let's go on and see how this applies to lattice walks. Okay. So I cut out a lot of caveats, but I can actually give you an explicit theorem that we can use. So this is by Ishizaki and Ogawara, doing different parts. If I can make myself a functional equation of this form, again, remember Q can be a number, right? It just something that has not a root of unity. If I can find something of this form, then I'm good. Then I know that either it's rational or differentially transcendental. Okay. So what I'm going to do is I'm going to use that solution of that kernel. I'm going to find a rational parameterization of that curve. And I'm going to be able to turn a natural generating, the kernel equation or a kernel functional equation into this form. Okay. So I'm going to start off with a natural functional equation, and I'm going to turn it into something of this form. Okay. So what I mean by rational parameterization is when I have a curve, I can give you an S and find a point on this curve where X and Y are rational. And we're going to be able to do this like using computer algebra. So this model here, I'm actually giving you a specific model. Andrew Becknitzer and I studied it, and we showed that it was not D-FINITE by showing it had an infinite number of singularities. But here's a totally different approach. If you study lattice walks, you almost always start with the same thing. You start with the very, very simple combinatorial recurrence that a walk is either the empty walk, or it is a shorter walk and you take a step. And then if you're staying in the quarter plane, you have to remove the walks that sort of went out of your region. So again, even if you can't follow exactly where this is, I will tell you for every lattice walk, you will automatically produce this equation. And it's just because of that very simple recurrence. A walk is a walk plus a step. I can rearrange this to what we call the kernel version. Now, the kernel strategies for functional equations go back to Knuth in the 1970s, and they've been extremely powerful, especially for using computer algebra techniques. But what it means is I move all my QXYs on the left-hand side. And on this side, I'm going to have these evaluations of my generating function, but they're different. They're somehow different functions. Okay. Here I see my kernel, my step sets, the inventory of my directions. Here I've drawn out, in this case, remember this is a specific example. It's not north, east, southwest anymore. It's what northwest, northeast, and southeast. Okay, there is a real points on that kernel. So you can see whenever I have a point for a fixed y. I have 2 points for any fixed y on my kernel. So that's going to give me a functional equation I can manipulate. And I'm not going to go through the details here, but you're going to see that it's going to be quite straightforward. I can turn my kernel version of the equation into an equation of that form that I showed you on that slide. Okay, so again, I would love to give you about 10 or 15 minutes to go through the details here, but the upshot is, as I have a picture of the kernel, I can see that I'm always going to have 2 points for a fixed y, and I can use that and a rational parameterization of this curve to actually give me that functional equation. Okay, so that's how Dreyfus, Ardouin, Rock, and Singer showed that this was differentially transcendental. Okay, so I hope that made some sense. Just saying that I'm looking at this geometric curve, and it's enough to turn it into one of these Q equations. So here I see, here my Q is this V squared. Oh, yeah, there's a little animation showing you that this is an infinite group here. That's just distraction at this point, I think. So Andrew Recknitzer and I, when we looked at this model initially, we did this very combinatorially. You can see combinatorially that you can, this is what an example of that walk would be. You get a directed walk in a strip, but the height is of continually of different heights. I don't know, we did a whole combinatorics on this, but we proved things by showing there was an infinite number of singularities. Okay, we actually used a strategy that he had used with, I think it was, I'm going to get it wrong, but I think it was Van Rensburg and Prellberg. For the self-avoiding version of this. Well, here in my walk model, I can go back and forth on myself. Well, if I can't go back and forth on myself, I have a self-avoiding version, and it's a little bit more complicated. But with Charlotte Ardouin, we can actually prove, her and I proved that, yeah, the self-avoiding version should also be differentially transcendental. And anytime you had something that was called by the iterated kernel method as a technique, you can probably use this method, this technique. Okay. All right. So I'm going to run out of time very quickly here. I just want to give you some hints of where things are going next. With my colleagues, Lucia Divizio, Gladys Fernandez, and Aline Bostin, we're looking at building a similar version of this, but now we're looking at algebraic interiors instead of just multiplying by Q or having that X over 1 plus X, actually allowing an algebraic transformation to try to understand the conditions of when things are going to become differentially transcendental. If we get that, there's a whole suite of functional equations that we can apply these methods to. There's a night's walk. This is a result of Uskemilou and Marko Petkovšek. Oh, I got to do this better here. There are some pattern avoiding permutations. This is one of pattern avoiding permutations, which was shown to be not D-FINITE. So I believe we can show that it's differentially transcendental, in fact. There's subversions of Baxter permutations, which also have functional equations, but it's a bit too long for this slide. And we're starting to capture the boundary between that D-FINITE, like the Baxter permutations had a D-FINITE generating function, and just seeing what you have to modify to boot you out into differentially transcendental. Okay. And then the goal is, of course, to understand the combinatorics of this. Why do these operators, what is a combinatorial interpretation of that operator? Okay, let me wrap it up. So the summary of what I've just said is that lattice walks are an excellent context for studying functional equations and this classification. So many things are in bijection with them, and they're very easy to manipulate. There are easy functional equations. Most class of D-FINITE generating functions actually are in bijection with some kind of lattice path model. So can we use that somehow to show Kristall's conjecture? And finally, I just want to emphasize that differentially transcendental classes occur when your ordinary generating function satisfies a second kind of equation. Okay, so there's lots of future work, simpling proofs, a lot of proofs that people have done to show things are not D-FINITE. They're digging into singularities, showing the singularities don't cancel, and it works, but sometimes it's not very enlightening, actually. Whereas I find if we can find the good operator, which shows you that functional equation that shows your differentially transcendent, I think that's much neater. I think that's a much better picture. So right now, that's one of my current projects with Lucia and Charlotte, is just to go through different functional equations and sort of show, yeah, you must be differentially, you're not just not D-FINITE, you're differentially transcendental, because here is that other functional equation that means you're going to be differentially transcendental. Actually, the generating functions for walks, the classification of the univariate ones is not complete. That could be completed. Regular graphs, they don't really fit into this picture so well. So how to unify the idea of the regular graph enumerations, that's another open problem. But mostly I want to find combinatorial mechanisms to demonstrate that differential transcendence. I think that this should be doable. Okay. And then just mining that geometry further. There's elliptic functions, it turns out, have been studied quite closely for many years. So we really should be using all that math that is behind there as much as possible in our study of generating functions if they do happen to appear. Whew. Thank you so much for your attention. This is such an ambitious schedule today, and I hope that I've given you at least some picture, at least one idea about what, if you're interested in things that are not D-FINITE, where you might look for that. If I can do that, then that's that's a success. Thank you very much.
That's great. Thanks very much, Marni, for that very interesting talk. And yeah, we're getting a bit past time now, but if there's probably time for a short question, if anyone wants to ask one before I hand over to the next speaker.
Yeah, a very quick question. This is Don. So Michael Wallner, a year or two ago, had a beautiful disproof of a conjecture of mine about walks such as AX bigger equal to BY bigger equal to CZ, where A equals B equals C is a really Young tableau. And I think he reduced it to two-dimensional walks using your result with. So it was a really beautiful thing. But I have another, I think, still open, be really nice. In a beautiful paper I wrote with Manuel Cabos that was stupidly and idiotically rejected by the algebraic combinatorics. And we made some beautiful conjectures that does not seem to be D-FINITE, namely the number of 3 by n Young tableau of shape n, and such that there is no runs of length more than 2. And we tried numerically, and it seems to be not D-FINITE. So it'd be really nice if you can.
I'll take a look at it. I've seen that paper, and you're right, it is a very nice paper.
Yeah, so I'm offering a prize of donation to yes. So it'd be really great if you prove it. And one last question. In this case, we don't know and suspect that it's not D-FINITE. The asymptotics is amazingly nice. In your cases where it's not D-FINITE, is asymptotics ugly, or sometimes it's also nice?
No, sometimes it's also nice. So it's the one that I showed, that example, the asymptotics are very nice. And
the connective constant mu is sometimes algebraic, like in our case?
Yeah.
Oh, okay, very interesting. Thank you.
Yeah. No, that's why it's good to have another. Yeah. No, that particular one, that the you can't show it by the asymptotics, but the asymptotics are very simple.
Very nice. Thank you.
All right. Okay. Thank you guys very much.
That's great. Thanks so much again, Marni, for that.
Oh, let me stop sharing.
Okay, thank you.